Hello everyone, myself Devangan Ghosh, and today I'll be explaining my project of data warehousing and mining to you. And my project is about automated defect detection for industrial pipes with the help of image processing and deep learning concepts of convolutional neural networks. So without wasting time, let's get into the project and let's go to my laptop screen. So coming to the basic data science libraries we're going to use is pandas for data handling, numpy for numerical operations, and matplotlib and plotly for data visualization. Coming to the first code block, we have used cv2 library for image processing, numpy for numerical operations, and matplotlib for displaying the images of the industrial pipes. Now coming to the code, this code is used for image processing, making image processing pipelines using OpenCV and Matplotlib to visualize the defects or the region of defects in the pipes. Coming to the first code block, and I think it's pretty clear that we are actually just processing the image of the pipelines and the defect regions of interest, and then from the image using our binary masks to classify them. Now coming to the second code block, this is basically used for the defect extraction process from the folder of images, the training folder of images, using corresponding ground truth for mask images. And the libraries which we have used in this is path for file path, obviously, cv2 for image processing, and numpy for array operations, and os for file handling. Now the types of images, the grayscale images are type B images in here, and the type B ground truth images are mask images with the defects. Extracted defects train, this is the processed images which will be saved for further project continuation. Now to apply the mask, we have used this snippet, this code of binary mask, and using cv2 threshold, and extracted defects for cv2 bitwise. This piece of code basically converts the mask to binary, applies it to the original image to isolate only the defective areas, and then it saves the defective areas with the name which we can see here is like abc0defects.jpg in the output folder itself. Now coming to the third code block, this script actually automatically labels the extracted defect images as either having a defect 1 or no defect, which will be classified as 0. So basically 1 for defect and 0 for no defect, and then save the model in the CSV file for further classification, further project continuation. And firstly, obviously, we load all the libraries and imports of cv2, os, pandas, and path. Then we save then we call the defect folder, specifies the folder where all defect extracted image are actually stored. We call that. Initialize an empty list labels to store images names and labels. Then we put on the loop through all the images, which assigns the labels based on their defect presence, reads each image in grayscale. Now we use cv2 non-count, count not non-zero function on images for non-black pixels. If any non-black pixel actually exists, the image has a visual defect of label 1. If the image is completely black, then it's labeled as 0 with no defect. Now then we save it to CSV. Then we create a CSV with 2 columns of label and image, and we save it with the name of defect labels.csv in the same folder. And getting a summary of this snippet, it helped us to prepare the label data for machine learning and deep learning, which we will be using to use on the train data set to train the model. and it also helped us automatically identifying whether the defect extraction worked or not. Coming to the next piece of code, we use it in PyTorch code for building the CNN, the main model for our image classification and detection. And we first import the libraries of Torch for neural networks, Optim for optimization like Adam and all, data sets and transform for image processing, and data loader for batching and shuffling the data for training. Now the CNN model, we named it as defect classifier, represents a binary classifier CNN, defect versus no defects. Then we have the convolutional layers. We define the convolutional layers over here, the self, convolutional, and sequential. This piece of code actually helped us to classify, to make two convolutional layers, that is, one for learning image features like edges and shapes, and other to reduce size and keep important features. Now then we fully connect these layers together. Then after that, after connecting, we forward pass it, which actually defines how the input flows through the model during training and prediction. Now this is a simple CNN structure which helps us to train on the extracted images grayscale and classify whether the image has a defect or not. Then coming to the next piece of code, the purpose of this code is to set up the custom dataset, the defect dataset, to load the grayscale defect images, resize and normalize them, read them from the CSV file, and return the image with the label pairs for training the model. The important libraries, firstly we import the libraries, define the custom dataset class, then we initialize the dataset and initialize the dataset length, load each sample, fetches images and label the data index. Then we use the unsqueeze function, which adds a channel dimension to make the shape, where in this case we have 1 by 32 by 32 for the convolutional neural network, convert the label into PyTorch float tensor, which returns one image and its corresponding label for each index. This output helps us verify that actually our data is properly loaded and is classified or not. Basically, use case, we would say we have loaded the data using data loader for batching, pre-processing for grayscale defect images, train the CNN defined earlier by PyTorch. Then coming to the next piece of code, we have the purpose is to train the neural network CNN to classify whether the defect is present in grayscale images or not. A custom dataset, which is basically running on the test dataset which we have in the folder. Then binary cross entropy loss and Adam optimizer. Firstly, we import libraries as always, then define the file paths, create the dataset and data loader, which is the defect dataset custom, which we have used the custom dataset class for loading the images and labels, and data loader, which the batches size are of 8, shuffled for training the randomness. Then define the model, loss function and optimizer. The defect classifier is the main CNN model. BEC loss is basically binary cross entropy, which gives the output of 0 or 1, defect or not defect, and the optimizer's learning rate is 0.001. Now we perform the training loop. We have 10 epoch full passes loops. After this, we achieve 0% of loss, which is pretty good. This means we have 0% of losses or entropies, which means we have like 100% information gain, which is very good for our model. This means our model runs perfectly. Now coming to the next code, we have basically this section helps us to extract regions from grayscale test images using binary ground truth mask and save the extracted in region in a new folder. Firstly, we import the libraries, set up the folder path, create the output folder if it's missing. If it's not missing, we have this true section. If it's false, then only it will create another one. Then we loop through the images, processes only .jpg files in test images folder, which is also the condition. Constructs mask name, converts file name from something like image3.jpg, and then we convert it to image gt3.jpg. This is basically the naming convention to identify easily which is actually tested on or not. Then we load the images, apply the masks, convert the grayscale mask into binary one. The same procedure again which we used for training the data in training dataset, applying the binary mask on the original image using bitwise and isolate the defect images. Then after all this, we save the result of the pre-processed image with only the defect areas visible, and finally we print the message which gives us the assurance that we have actually trained the model, or we have actually trained on the test dataset. This helps us in matching the test images with their mask, extracting and saving defect regions. It's like cleaning a pre-processing step before applying the any test time classification or analysis of those defects. Now coming to the next code, we have the test defect dataset, which is used to load and pre-process grayscale test images from the directory itself into the format suitable for feeding into PyTorch model, typically used in the testing phase. Firstly, we import the libraries, then class definition datasets used to build the custom dataset for test time predictions. The methods, we use some methods like init length and get item. This basically does is, so this functions actually helps us in storing the test images directory, collect all the JPG file names and required PyTorch data loader to work properly, loads the test images index and normalize the pixel to 0 and 1, convert the PyTorch tensors and add channel dimensions for CNN to work properly. And basically this code blocks helps us in efficiently loading and pre-processing the test images, making them ready for the trained PyTorch model and returning both the image name and tensors. Now the final code block is all about prediction loop results in an empty list. Now basically we have loaded the model, trained it, and now it's time again to load the model on the test dataset, where we have used the code block of torch no_grad function is used to disable the gradient calculations, and the loop goes through each images in test datasets and gets the output. If the output is greater than 0.5, it is classified as defect 1. This means there is a possibly defect in that image, and the prediction is stored in a file in the image name of results list, and then the prediction is stored in pandas data frame, and the data frame is stored in the CSV file, which is the defects prediction CSV, which contains all the images name and corresponding precisions. So basically it gives the final results after the predictions. The message is print of confirm the file is actually saved. So this was all about the project, and I hope I went a little fast because the project is pretty big to explain it line by line. So I explained major sections of each code block and the working. Thank you.